Hi, welcome back. This is Mr. Yeager again. We're moving into our next section on energy. In our first section, we looked at the idea of energies within a system, and that creates what's called the potential energy of the system, whether it's gravitational or elastic potential energy. We also looked at kinetic energy, the energy of motion. Kinetic energy does not need a system. It can be the individual object itself that has that kinetic energy. And we finished the last section on the idea of, okay, if I have these types of energies now, how can it change from either amount or from one type to another? How can it change from gravitational potential energy to kinetic, or kinetic back to gravitational? All right. And so we said we have to add a force, apply a force to the system itself, or the system has to apply a force to its surroundings. And so what that leads us to is this idea of work, this concept of work. All right. And so this is where we're going to put force and energy together. It's going to create work. And so the definition of work is when a force is exerted on an object and makes it move parallel to the direction of that force. Okay? So it requires two things. It requires a force and it requires a displacement parallel to that force. That's going to be very important, that idea of parallel. All right? So we need to put those together. So it's a force and a distance. All right. And so this is our basic formula. Work equals force times change in distance parallel. F times D. All right. F times D parallel. Now that is one of those formulas that is given to you on your AP formula sheet. Okay. If you look at it, it is work equals force times D parallel. All right. Work is a measurement of joules, because what we're doing here is work is a transfer of energy. All right, that's another way we look at it. If you look at the AP formula sheet, you'll see delta E equals work. Work creates a change in energy. All right, within the object itself, within the system itself, or over the whole system completely. All right, so we're going to need work, force, and distance to complete these particular problems in order to see that work is actually being done on an object. Okay. So, there's a couple things we have to make sure we understand, all right? And where people slip up when they do these problems. Force must be in the direction of motion to create work. If it's not in the direction of motion, no work is being done. All right? No work is being done at all. So we must have it move in the direction of motion. All right. Now, this is one of the little tricky parts. We're going to talk about how there's positive and negative work. When the force and direction are in the same direction, the distance, the displacement change, let me say that again. When the force and the displacement are in the same direction, we will say you're doing positive work. We're saying you're going to do positive work. That's very important. Vice versa, when forces act opposite to the direction of motion, if forces are being applied back while the object's moving forward, maybe you're trying to slow the object down, we will say that you create or cause negative work. Okay? So when they're in the same direction, force and displacement, it's positive. When they're in opposite directions, we're going to say it's negative work being done. All right? So if I ask most students and go, okay, so is work then a vector quantity or a scalar quantity? Most would then say, based on this definition, it must be a vector quantity, because we're going to have some sort of number with it. Okay, we're going to have a number, but also what seems like a direction. If you recall to all previous chapters, the positive and negative signs is simply a direction, and a vector quantity is magnitude plus direction. Okay? But here's one difficult thing. Here's one difficult thing here. Okay? Oh, forgot to say. We already mentioned it though already. Forces not in the direction of motion create no work. And we're going to run into that. This is going to be important still, where we need to draw free body diagrams. All right? We cannot get away from that. If we're doing some problem that has some forces involved, you must draw the free body diagram. So now let's move forward. Thing is, work is actually a scalar value. Energy and work are scalars. All right, what does that mean again? That means it's magnitude only. All right? There is no direction to energy, which if you think about it, I mean, you don't sit there and go, oh, my energy is increasing to the right. It's increasing to the left. It's increasing up or down. No. The energy is increasing, the number is increasing, but there is no direction to energy. All right? And that's something that's going to come up quite a bit that might cause some confusion. There is no direction to energy. It is simply a scalar quantity. All right? So, what do we mean by the positive and negative signs? Because we actually do want to use them. We need them. It's going to be very important in our large work energy theorem formula. And so what do they mean? When we say something has positive work, that means the work is being done on the object or the system. All right? You are increasing the energy of the system or the object. If I try to start pushing a box forward and it starts moving forward, it'll start moving faster and faster and faster, which means its kinetic energy is increasing. The box's kinetic energy is increasing. That's because I apply a force, I push, and I move in the same direction. It'll speed up. That's an increase in kinetic energy. I'm doing work on that box, and therefore creating more energy within the box. All right? So energy gets transferred to the system when we say it's positive work. When it's negative work, it's often defined as saying that the work is being done by the object. It's being done by the object. All right? Now that's confusing for some people going, okay, how would that box be doing work? If I keep pushing that box, and think about what happens when I stop pushing the box. If I shove it hard one time, it might slide for a little bit of distance, but it's going to slow down, which means its energy is decreasing. What is the box doing work on? All right, and the answer to that would be the floor. It's the frictional force that's acting opposite and therefore decreasing the energy of the box. So sometimes we like to clarify this a little bit more and go that energy is being transferred from the system. That frictional force between the box and the ground, the box doing work on the ground, it is transferring that energy to the ground itself. It's coming from the box, and that's why it slows down eventually. So positive work, okay? Positive work is saying that energy is being, basically, like it's kind of being shown there, added to the system. Negative work means energy is being pulled from the system. So again, that's not energy that's just lost forever. It's going out to the environment. It's going out to the universe. However you want to keep on saying that. We usually will just say environment. We don't go so large as the universe. All right? But that's what's going on. All right? And when we have positive work, something must be acting on the object to make it move faster usually, or make it go higher on my shelf in my room. I have to lift that object up. I'm transferring potential energy. My own energy is being changed into potential energy for that particular object. Okay? So, before we jump into this one problem, I want to do one real quick example here. Okay? So just ignore the problem on the board here. Let's say, for instance, that here's me. Okay? There's my wonderful drawing to learn I can't draw at all. Okay? Let's say I'm pushing against a wall. Okay? I'm applying a force against a wall. All right? This is a classic old, beginner work problem. All right? So I can sit there and be pushing against that wall. I push and push and push and push. All right? I get, tired. My face turns red. I feel like I'm doing a lot of work trying to push this wall. The thing is, will I ever move that wall? Of course not. Okay? Of course not. The distance the wall travels will be 0 meters. So how much work will I have done if I ever try to just push an object forever and ever and ever? Okay? The answer to that would be F times 0. Guess what? It's 0. Oh, not newtons. Oops. Joules. Sorry. All right? There'll be 0 joules of work done on the wall because I didn't actually ever get it moving. So that's one quick example. Okay? We don't do any work when you just push an object but you don't move it. The object has to be moving. All right, let's get to one that's more AP Physics level. Okay? So we have this problem. A string applies a 10 Newton force to the right on a 2 kilogram box on a frictionless surface for a distance of 50 centimeters. Okay? So force is being applied to an object, and it's moving 50 centimeters across a floor. Okay? How much work is done? So looking at the initial problem, we're going, okay, I want to do work equals force times distance parallel. All right, I want to do force times distance parallel. And so I want to try to just break this problem down, which I have on the next slide. Okay? Okay. So what we try to do, I can give you some basic steps to solve. This is just recommended. Draw out a free body diagram for the object. All right, we have a box. All right, what forces are being applied to that box? Because a lot of AP problems will be asking about forces not pointing in the direction of motion. All right, which remember that means it's zero. So we want to draw out the free body diagram so we can understand why are they asking about the weight? What work is being done by the weight? That seems like a weird question, but it's one that might be done. Okay. I recommend drawing the direction of the displacement vector. Okay, it says I would assume the object is moving to the right. Okay, it's on a frictionless surface, so it should move to the right. Make sure that displacement vector is not on your free body diagram, but that'll help you understand what's positive and negative. And then find the net force that the object experiences in the direction of the displacement vector. Okay, what would be the net force? So here's the problem, already broken completely down. All right. If we look over to the side here where I have my free body diagram, okay, you can see here are my three forces acting on the box. I got tension, I got normal, and I got weight. That would be the official free body diagram. You can see I also wrote down the displacement. All right, that's just to help me go, okay, should tension be positive or negative? Or if I have to justify, why is the normal creating zero work? There's 0 joules of work from the normal force. Well, that's because the normal is perpendicular to the displacement. All right. So the only one that I'm really interested in then, I can ignore the normal and the weight, is the tension. All right. And so only the tension will create work. And so what I do is, this is a pretty easy problem, probably a little bit too easy for AP, but still trying to break it all down. All right. All I have to do is, I use the formula, work equals force times distance parallel, work equals 10 times 0.5, and that'll equal 5 joules. Now the thing is, technically I would just leave it as 5 joules, but now I want to be specific and go, is it positive or negative? Okay? And so I'd say it's positive because the displacement is in the same direction as the tension. That means the object must be gaining energy is another way to look at it. I am putting 5 joules of energy into the box for it to use however it wants. Okay, most likely in the form of kinetic energy. All right, looking at problem number 2. Basically, we're adding friction on in now. If we add friction on in, so a string applies a 10 Newton force to the right on a 2 kilogram box, dragging it at a constant speed. If you haven't figured out, those are 2 very important words to catch on to in AP problems. All right? It's moving at a constant speed across the floor for a distance of 50 centimeters. Calculate the work. All right. Constant speed. What does that mean? That means the object must be in equilibrium. Which means all forces must be equal. Left and right, up and down. The object must be is in an equilibrium state. And so that's how I know now that there must be friction present in the problem. If there was only tension, there'd be no counterbalancing force there. Okay? So tension and friction are now in the direction of displacement. What I mean by that is they're both parallel with the friction and with the displacement, friction and tension. They are parallel with the displacement, which means tension will do work, friction will do work. But will the overall energy of the system increase? Okay, let's think about this. Well, if it's moving at constant velocity, that means the tension must equal the frictional force, which means the net force is 0. So what's the actual amount of force being applied to the object? The answer to that is 0. All right? They never write it up there, but again, the formula should technically be, and this is where I say net work, would be the net force times the distance it travels. It still travels a distance. I would technically include that in my formula, but anything multiplied by 0 is 0. What's happened here is I could say tension is going to do 5 joules of work, positive 5 joules of work, but what's the friction doing? The frictional force, the work by the frictional force would be negative 10 newtons, because it's in the opposite direction of motion, times 0.5, so it's going to do negative 5 joules of work. Well, if I add positive 5 and negative 5, what do I get? 0. So any work that I'm adding to the box is being released by the box through the frictional force, and so the overall amount of work done on the object would be 0. What do normal and weight do? Absolutely nothing. They'd be 0 work as well. All right? So the thing that you're going to run into quite a bit with these problems is you've got to pay attention. Are they looking for the overall amount of work on the object, or are they looking for the amount of work on one force versus another force? If they said, does tension do work? The answer would be, yes, that's true. It does do work. Does the frictional force do work? Yes. What type of work? Negative. But the thing is, if it's moving at a constant speed, these two forces are equal. The forces are the same. The distances are the same. They're equal opposite amounts of work being done, so 0. Now, what if I move at an angle? Okay, what if I push or pull at the object with a force at an angle? Okay, and this is going to relate to inclined plane problems and pulling and pushing. All right. The thing is, the formula is work equals force times distance parallel. Okay, I could rewrite this and say the parallel force times the distance. I just need to have them in the same direction. That's all we're basically saying. All right. So that's what we're going to look at. If I have this angled force, all I want is the parallel component of the force. All right. And so that's pretty easy to do. All right. They actually make this pretty consistent. All right. If you're given this particular free body diagram, okay, what force matches the displacement? All right. Technically, right now, okay, I guess we're also again assuming that there is no friction at all. I can draw in the weight and the normal. But the thing is there any force pointing exactly in the direction of motion? And is there anything parallel with the displacement? The answer to that question is no. There's nothing perfectly together. Now, if I said which force will do work, the answer would be the force applied is doing work. But should I use this particular force? So if this was 10 newtons, would I be plugging in 10 times displacement? The answer to that is no. I would not do that. What I need to do is I need to find the component. I would find the FA, what I'm going to call X, the horizontal component of the force. This right here is the official force or component of force that is actually going to create work or cause work, right, in this particular problem. The thing is, in almost all these problems, this is always going to be, usually with the angle that they give you, the cosine, the adjacent side of the triangle, which means the force parallel will equal the applied force times cosine theta. All right, if I do good trig. And so, therefore, we often write the formula for work as F cosine theta times D. All right, or on your AP sheet, FD cosine theta. All right. The thing is, if there is no angle, if the angle was 0, so you're pulling it perfectly horizontally, that means cosine theta is 1, so guess what? Work equals F times D. Okay, that can be eliminated. So this is technically the more effective, efficient formula. It's just we know if you're pulling it horizontally, cosine theta is 1, and so it's just work equals force times distance. So it's always going to be that horizontal component that we're looking for. All right? And it actually, as we said, basically works in all situations. All right? Pulling an object at an angle, pushing down an angle, going up an inclined plane. Okay, it can actually work. In all these cases, what you need to make sure you always remember is that the force must be in the direction of the displacement. Any other force out there, okay, any other force will cause 0 work. So we always write 0 for those. All right, so for inclined planes, right, if you have a problem with saying what's the work done on an inclined plane, let's get this out of the way so we can see it a little bit better here. Okay. Determine the work a hiker must do on a 15-kilogram backpack to carry it up a hill of 10 meters. These problems, they usually cause a lot of problems. People are sitting there going, wait, you know, are we looking at how far you're carrying it? Or I just don't understand how you're doing work on the backpack. Okay. What you need to think about most here, okay, and this is a tough one, is which way is the backpack exerting a force? And therefore, which way are you exerting a force against the backpack? What you have to think of here is, if you have the person, here's my wonderful drawings again, they have a little backpack on, there's their backpack. The backpack is only going to exert a force straight down. So you have to think about what's going on here. If the backpack is exerting a force straight down, and I move straight horizontally, I'm not looking at the inclined plane right now, is the displacement and the weight, are they parallel with each other? Okay. The answer would be no, they're not. So if I just simply carry the backpack from one classroom to another at school, are you doing any work on the backpack? And the answer is no. So the thing is here, we have to think back. If you simply carry an object, you do no work. All right? If you simply carry an object, all right, and move horizontally, let me make that clearly. If you're just moving horizontally, okay? But if you start climbing up a hill, now which way are you applying a force? If you're climbing up the hill, you're going to have to be lifting the bag up. You're bringing the bag to a higher height. Think about what we're changing here about the bag. If I increase the height of the object, that means, hey, guess what? I'm increasing the gravitational potential energy of the object. How am I doing that? I must be applying some work on the backpack. So it's not about the fact how far you're carrying it, it's how high you're carrying the backpack up the inclined plane. All right? So basically this is what I just said. All right? We're only going to be looking at the vertical forces and vertical displacement. Anything else horizontal is going to be basically ignored. All right? Sure, you might be doing the work on yourself if you're running up that inclined plane, but the idea is you start at rest at the bottom of the inclined plane, so what's your kinetic energy? 0. You finish up at the top of the inclined plane, your kinetic energy is going to be 0 because you're at rest. So the only change in energy must be the change in height that occurs. All right, so we're going to ignore everything else. All right. The thing is, a lot of these problems, they're going, oh, there's no angle. Should we need an angle? No, it actually doesn't matter. Who cares about the angle of the incline? We only want the height of the inclined plane. All right. And so I take you back to the more simple form of the formula, work equals force times distance. All right. But the thing is, in this particular problem, the force being applied is the weight. You are overcoming the weight. Okay? Force will equal the weight. All right? You are carrying the object up with a force, up the inclined plane, okay? While the weight is pushing it down. So what do? You are moving up displacement with a positive force. The thing is, it's not like that bag's bouncing around on your back. We're going to ignore that if it is. All right? And so F must equal the weight, which is mg. What is the distance that you cover? That's going to be the height. All right? That would be the displacement, would be the height. So guess what? Work equals mgh. Work equals mgh, which we'll probably go over this a little bit more detail later. Mgh is the potential energy, which we denote U for some reason. A lot of times I just write GPE. But AP Physics and Physics uses U as the symbol for potential energy. U equals mg delta y. Again, I use H instead of delta y. So work is equal to basically the change in potential energy. You're changing the height of the object. Okay? So that's why we finish this up and go, guess what? We only care about the height. We can multiply all those things out and find just the change in height. All right? And so I put all the pieces together and I get 1,500 joules would be the work being done. So one last thing about inclined planes. Okay? Does the change in energy matter how steep the hill is? In other words, there's two ways up to the top of a mountain. There's a long, more gradual incline, and there's a much steeper incline. Okay? Which one will have a greater change in energy by the time they reach the top? The answer? Neither. Okay? I don't know if you know switchback trails. That's the idea where we try to make it easier to walk up a trail so you go back and forth quite a bit. But the thing is, it doesn't matter how you reach the top. You can go a switchback trail. You can be that person that tries to cut the trail and goes straight up a steep part of the hill. But in the end, their final energies will be the same. Okay? Their overall final energies will be the same because they have the same delta y. Delta y is the same as long as they have the same backpacks. All of that's the same. It'll be the same change in potential energy. So that they like to ask again that question of, does any one person do any more work than the other one? Okay? On the backpack itself, no. Is it possible that the person themselves is exerting more work? Absolutely. Okay? That's why we have to make sure and go, what are they asking me to figure out the work on? If I'm talking about the person, well, guess what? This person obviously has a lot longer to go, and they might have friction acting on them for longer. While this person trying to zoom up the steep slope, they have a much shorter distance, okay, up the slope. Now I'm looking at the distance like this, okay, actually along the slope. There'll be less force of friction being applied over a smaller distance. Actually, sorry, we could have the same amount of force of friction, but over a smaller distance, so less work being done on the person. So, I know it's confusing. We got to pay attention to what they're referring to, what is the work being done on, and then basically answer the question from there. The only other thing in this particular part, I know we're going a little long here, the only other difference is possibly how quickly they apply that work. And so that gets us to one last topic, and usually AP tests only asks like one question about this, so we need to know it. And that is over power. Okay? At least the last 2 years, I feel like I've only ever seen one question on power on each test. So, for power, like I said, you only need to know how to do the calculation. Power itself, the definition is the rate at which work is applied. We're saying how fast is work being done. And so, therefore, the formula is the amount of work being done divided by time. How quickly are you doing that work? The unit for work, the watt. You really don't need to do that much more with power other than that. So I think I have one problem here. So the person with a 10 kilogram backpack zooms up a 10 meter hill with a 30-degree incline. In 10 seconds, the second person goes up, chooses a steeper trail, and they finish. Let me get this out of the way so we can actually see it. They finish up the hill in 5 seconds. Which person applies more work? I should say on the backpack. The answer would be, they're the same. But which one will apply more power? Well, if they have the same amount of work, the one that does it faster will have more power. Okay? Which I I think we have our work right here. So both backpackers apply the same amount of work on the backpack. Okay. They both have the same height they're covering. It ends up being 10 times 10 times 10 based on the math. All right. The thing is, in terms of power, I would then divide that 1,000 joules divided by 10 seconds. So one backpacker does 100 watts of work, while the other one is doing 200 watts of work. Clearly double because they're doing it half as quickly. They're doing it with half the time. All right. And that's it for today. So, work must be force and displacement in the same direction. Positive if they're both pointing exactly the same direction. Negative if they're pointing opposite. Zero work if it's not pointing in the direction of motion. And then on inclined plane, we're only interested in the change in potential energy, the change in height with the objects. And then finally, power is the rate at which work is done. Thank you.